Okay, so welcome to chapter 2 of the course. The task of this lecture, it's a 2-hour lecture. In the first half, we're going to construct the integers, and we're going to see how far we can get with that. If you looked at the second problem set, you'll see that the construction of the integers isn't really part of the evaluation for that assignment. That doesn't mean that this is not a topic that will be covered in the final exam. It simply means that most of the questions or exercises that you could come up with in the context of the construction are rather technical, and you wouldn't necessarily learn that much by solving them as a problem set. But I will still give exercises during the lecture that, as I mentioned, are good candidates to be on the final exam. And also, it's a great opportunity for you to understand what is actually going on, right? Because there's this disadvantage of seeing someone else solve things or write proofs, and that is that it makes perfect sense until you try to do it yourself. And then you realize, well, you can't really reproduce the proof. Does that mean that you didn't memorize it, or that maybe you didn't fully understand it in the first place, right? And this is something that happens to everyone. I'm not trying to refer to, like, we're all students, what I'm trying to say. Okay, so this is the second chapter. Let me share my screen and we'll get started. As promised, the integers are constructed as a quotient. And we haven't really seen that many examples of a quotient, so this will be the first one. Let me add some details here. This is chapter 2, which I think I called the integers. And so those. And the first part of the chapter is, of course, construction. Or maybe I should say integers. Integers are a quotient. A quotient on what? I think I said a quotient on the natural numbers. We have to be a little bit more specific than that. So what's the motivation? Why would we want to construct the integers? And here's one of, a problem that may arise when you're trying to learn more abstract math, and that is that you learned about the integers when you were probably in elementary school, right? Probably the first time you learned to subtract, maybe at some point someone told you, well, if you think about money as a debt, then you can make sense of having a negative amount of money. And then you can subtract, and then you can do all sorts of stuff, right? And then you might be learning how to multiply these numbers, and you might be getting stuck or being confused about the fact that if you multiply two negative numbers, you get a positive one. Well, that's really harder to understand with the analogy of debt, right? Because what does it mean to multiply times a negative number in the first place? And multiplying two negative numbers gives a positive one. Now, the reason that you're probably not confused about that anymore might have more to do with the fact that you're used to it rather than you fully understand the inner workings of whatever model of integers we're constructing. And this brings me to my next point, and that is, if I gave you a completely new structure that you've never seen before, we would probably be just as confused as the first time that we were introduced to the integers. So this is why constructing something formally is important, right? Because it tells you, it answers the question, does this structure exist in the first place, or is it just something that we're making up? And the answer to that is, well, yeah, we're making all of this up, but it still makes sense, and it actually had there's a ground to all this, which is also something I motivated, I think, a couple of weeks ago with the Baron story. So algebraically, we are interested. A lot of these structures that are mostly algebraic, right? I mean, there's obviously set theoretical properties to these things, topological properties, but right now the most interesting one is probably in terms of algebra, in terms of what you can do with the operations and with the numbers, right? We are interested in newer structures will have more interesting properties in terms of the other more perhaps more advanced subjects. But right now, we only care about algebra more than anything. In solving equations, but there's equations that we can solve, right? For example, something of the form a plus an unknown number x. This may not have a solution in natural numbers, right? So in n, for instance, this doesn't always have a solution, right? Something like this really has no solution. No solutions. This is a very simple equation, right? It's just one produced by addition. But if we can't even solve this, well, our structure is not very strong in terms of algebra. So we want to solve equations like this one. And later, of course, we will introduce more complicated equations and a new structure to try to solve it. Now, the takeaway that I'm going to hopefully teach when I do these constructions, it's kind of a spoiler alert. Every time we expand or construct a new structure, because of course this isn't just about the integers, right? We will be expanding this to the rational numbers. There will be a detour, of course, to number theory. I won't do this all in one class. And then the real numbers. And then I think we'll briefly mention maybe the complex numbers and so on. Every time we add a new structure, we gain properties. For example, we gain a way to solve equations. But every time I expand, I'm also losing properties. So for example, from this, every time we expand a new structure, we gain properties, useful properties. Solutions, for example, these solutions. Oh. But we lose others that are also useful. For example, from the natural numbers to the integers, we lose a very important property, which I mentioned is the most important property, maybe not in terms of algebra, but in general, of the natural numbers, and that is the well ordering, right? The fact that you can do induction, you can do that on the natural numbers, you cannot do that on the integers. Maybe you can do that if you divide into cases or using some tricks, but not in general, right? So there's no induction in the integers, and there's more equations that you can solve with the rationals than you can with the integers. But there's properties that you lose as well, right? So I won't talk about that because we will construct the rationals in a future chapter. So this is like a spoiler alert. It's not just that you can find a big structure that solves all of your problems. Every time there is a trade-off. Actually, that's a better way to summarize this. There is always a trade-off. There's an intermediate structure that isn't really extended here, which is the modular arithmetic. That will be something in the middle here. I can't really include this in this list because it's kind of different, right? But anyway, just so you know. Okay, so let's get started with this. How would we construct the integers? How do we make sense of subtraction? Subtraction makes sense sometimes, right? For example, I can definitely make sense of this in the natural numbers. I can make sense of subtracting 3 from 5 and getting a natural number 2. But this doesn't mean subtraction is defined, because subtraction as an operation, as a binary operation, if you recall the definition from last week, should be defined everywhere, should be defined on every pair of whatever elements in the structure that we are considering. This is not the case for the natural numbers, and what that means is we don't really have a subtraction, a general subtraction yet. So the idea is as follows. So let's just start the construction and see where we get stuck, okay? So first definition. I will define a difference to you. This basically captures the abstract idea of subtraction, right? Okay. So definition 1. difference in a pair of natural numbers. So an element of n cross n, right? So this isn't going to be a quotient on n specifically, it's going to be a quotient on n cross n, which just makes it a little bit more different, more complicated. So what do I mean by difference? I want to make sense of subtracting n from m, right? So let me add some comments, which I'm adding in green. I think that helps. So this thing dreams of being m minus n. Of course, I can't write that yet because, well, I haven't defined what that means. But this is what this element is going to represent. And I need to talk about everything that I'm going to need about subtraction without, of course, saying what subtraction is yet, because I haven't defined it. It's what I'm trying to define, right? So, like I said, a big aspect of this course is an invitation to more abstract math. And if you learn how to do these sorts of constructions, well, you can do this on a lot of other contexts too, right? The integers, of course, have already been constructed. Like I said, we've talked about this since elementary school, but there's many other structures that are useful that you might come up with, and they might solve problems that no one has solved yet, right? So this is definitely a useful tool that you must know. Maybe I'll give some examples of quotients like this, which are not as common or as famous as this one, that can be used to solve some interesting problems. So a difference is a pair. Actually, that's it. Difference is a pair. I'm just going to call it difference. Of course, there's nothing special about it. Now, a difference is positive. Mn is positive. This is the word I'm defining. Positive difference is this, right? When you're taking a big number and you subtract a smaller number from it, well, in this case, you would even get a natural number, right? So this is called a positive difference. Now, just as a reminder, what does it mean? This is the order of the natural numbers, right? The order that we already know, that we already defined. So that just means that there is a natural number a that is positive, right? So non-zero, such that if I add it to the small natural number, I get the big natural number. Right? That's the definition that we gave of the order. That's how you define the order in a natural number. This is the strict order, which maybe I haven't mentioned before, but of course you're just removing the possibility of a being 0, and thus n and m being the same number. Nothing special there. And finally, if two differences, m and n, I'm going to define this relation on these pairs. Let's see, what other letter can I use? Let's say PQ. If and only if and only if. I shouldn't have to write if and only if, right? All definitions in math are if and only if. So I'm defining a relation on pairs, on differences, where I say that two differences are the same if what? How do we make sense of this? So here's the idea. This is supposed to be representing m minus n. It's the object that I'm going to define. I haven't defined it yet, but this is what it's going to be ending up behaving as, right? And this is p minus q. So if I'm trying to define what it means for two of these objects to be equal, how would you define this if you had no idea what subtraction is yet? If you don't know subtraction, can you maybe rewrite this thing in terms of operations that we do know? These are natural numbers, right? So we can add them. What happens if, for example, I simply solve for one side, q on both sides and n on both, sorry, if I add q plus n on both sides. Yes, exactly. Okay, I got this answer from the chat. Thank you. right? So the expression in green, or the one in parentheses, the top sentence doesn't make sense yet. I haven't defined subtraction, right? So that doesn't make sense yet. But the one below makes perfect sense, regardless of who the the four natural numbers might be. Because I'm just adding things and comparing them, and I will always get a natural number, right? So that is the way to define this equivalence relation, which is capturing the idea of two differences being equal, right? This makes perfect sense. So the first statement, which I think I'm just going to write as a lemma, since it's not really that important, just going to be like a stepping stone or something else. If you think about it, the way math is structured, or at least these proof-based courses, is you have a statement and a proof, a statement and a proof, maybe some examples in the middle, but statements are cataloged in different ways depending on the role they play in the text, right? So lemmas are stepping stones to theorems. Propositions are like less important theorems. Theorems are, of course, bigger statements that you're going to use to do other stuff. Corollaries are consequences of those theorems, and I think those are the basic ones, right? Am I missing one? I mean, there's other names that you can use, but that's not really that important. In the end, they're all just theorems, right? Okay, so the first lemma, which I think you can expect, is that this relation that I just defined, which is like a difference relation, right? By the way, in today's quiz, there's a question about this, and I'm calling this relation being D-related, I think, or D-equivalent. This is just because when I'm typing out, I cannot use these symbols. It's not that easy. I don't have math script, I think, on purpose. So anyway, D-related, right? So this is an equivalence relation. Of course, it should be, right? It's supposed to represent the equality between integers. This is an equivalence relation. Now, since we haven't done this a lot, maybe we should do this proof. This is an equivalent relation, so we're going to prove this. Most of these proofs are very technical, and they're not really that deep, right? The deep part is, of course, the construction in the first place, the fact that this works. So don't get too hung up on the proofs. I will add a lot of them as exercises, so that you should do them in your own time to make sure you understand what this is, and also to make sure that there aren't any mistakes in the theory. Okay. So how do you prove that something is an equivalence relation? Reflexivity is the first bit. So let's just say I'm going to prove reflexivity. How do you prove reflexivity? You want to show that every element is related to itself, right? So m plus n is obviously the same as m plus n. And that means that this tuple, this pair, this difference is related to itself, right? Okay, reflexivity tends to be the easy ones among the not too weird relations. Should be symmetric. How do we do that? So if AB, should I call it maybe the same letters, MN, is D related to AB, then by definition that means that M plus B. If I don't mess this up, just let me know if you see a mistake. Okay. Obviously, I can just flip the order of these things. So obviously, N plus A is also M plus B. Thus, I get the same thing backwards, right? So this isn't really very interesting, like I mentioned before. Okay. And transitivity. That tends to be the trickier one among these simple definitions. How do you prove that this is transitive? This will take some more work, so I'll assume that Mn is D related to PQ, and PQ is related to what? RS. So what does it mean? It means that m plus q is the same as n plus p, and that p plus rs, sorry, is the same as q plus r, right? So how do we combine all these things? Well, you just have to be clever about it. Why don't we add s on both sides of the left equation, of the left equality? So we have this s on both sides. But of course, addition is associative, so I can just put parentheses here wherever I want. That's something that is written in a theorem of the last chapter. I don't have to convince you this is true. And p plus, actually, sorry, it's associative and commutative, right? So what I want is, of course, p plus s. So this I can just substitute by this thing right here. And what now? Let me see. Just do this. I can cancel q on both sides, right? There is cancellation in the natural numbers, even though there isn't subtraction yet. But of course, I can cancel stuff. Finally, m plus s is the same as n plus r, or written in the language that I just introduced, this should be mn derelated to rs, and we're done. Okay, so like I said, these proofs can get a little bit tedious. It's not really that deep. Now, there's another lemma that is not too crucial, and I'm not going to prove this. This is actually part of the quiz for today. So another thing is that I defined two things, right? Not just this equivalence relation, but I defined, what did I define? Oh yeah, a difference is positive if something happens. So of course, if this is going to be a quotient, I want the elements of the quotient to be positive or negative as well, right? That's the whole point of me doing this. The positive will, of course, be behaving the same way that the natural numbers do, and the negatives are the new stuff, right? That's the new thing that I'm adding. So if I want that to be true, then positivity should be independent of the representative that you use to pick this thing. So maybe before I do that, let me give you an example. So here's an example, and by example I mean I'm going to just write a few random things that hopefully make sense, right? So there's a number that represents the number 1, right? Let me think about this. So the number 1 of the integers is represented as a difference of the number 1 and 0, but it is also the same as the difference between 2 and 1. And by the same, of course, I really mean equivalent, d-equivalent, right? And this is the same as 3, 2, and this is the same as 4, 3. So there's infinitely many representatives for a given integer, right? There's many ways of achieving the same difference. A lot of infinitely many differences will always be equivalent. So the question is, I'm defining what it means to be positive. Well, that shouldn't depend on the representative, right? Because of course what I want is to ignore the representatives. I only care about the difference itself. The first lemma is if you pick two different representatives, possibly different representatives. So let's say that you pick PQ, and that's a Q, and M is positive. Then any representative, PQ, must also be positive. So is PQ, right? So positivity doesn't depend on the thing you're picking. And here is the most important property about this. So if Mn is positive, look at the example about positive. Look at the example in green. I can always do this, right? I can always pick this representative that is easier to explain than the others, right? If I give you really large numbers like 123 and 122, well, sure, that difference represents the integer 1. But why would I pick those? Why don't I pick the easiest, which is always the one that already has the integer represented as the first coordinate, namely 1. Now, of course, the coordinate is a natural number, and the thing I'm defining is an integer, which are not the same thing right now. So if m is positive, then there is a natural number n. How do I write this? There's a natural number that is not 0 because it's positive, right? And that is this, such that mn is represented or equivalent by p0, right? So I can always, if I have a positive difference, well, then that's basically just something of the form p comma 0, right? You don't need two parameters to define a positive difference. Why? Because positive difference already exists in my universe. They are already part of the natural numbers, right? So there's no need to add more things. So proof 1, this is today's quiz. I will give you a few minutes after I write this down for you to solve this. Should already be answerable on Quirkus, if I'm not mistaken. And the second one, okay, should we do this proof? Yeah, let's do this proof as it might be useful, right? So if mn is positive, that means that m is bigger than n. So there is, yeah, this is a bit too easy, but anyway. So there is a positive number that represents that difference, which is a natural number, right? So there's a positive number such that the small one, which is n plus p, is m, and I can just sneak in a 0 on both on the second side, right? And that just means what you think it means, right? So this is d-related to p comma 0 because, well, that's how I defined it. So that's a proof. Very easy. The one you have to do is just as easy. Now, okay, this tells me how the structure works, but these are the elements. How do I work with the elements? I need to know how to add them and how to multiply them, and finally how to subtract them, right? So maybe let's do a brief pause right here. Yeah. So now I have to define the two operations, and I won't spend as much time doing that since it's just routine arguments by this point. There's nothing new about this. So I need to define two things. How do you add two differences, right? So if m and n are two differences, I'm going to add them by what you might expect, right? Just coordinate-wise. I think this doesn't really require a lot of motivation. You think about what these things mean, right? This is going to represent this, and this is what I'm trying to define. So if I add two of these things together, well, this is just n plus p minus n plus q, right? Right. So this is what this is representing. Let's add it like this box. Okay, so this is how I define addition. Now there is something that you should always verify, and we won't verify this time because I think it's kind of tedious and routine arguments. We might verify this for some of the other structures that I will define. How do we show that this makes sense? And by that I mean, if I give you two representatives and I tell you, can you add them up and tell me what I get? You might be hesitant and say, wait, how do you know that the representatives that you picked will always produce the same result if someone else picks a different representative? Because in the end, I want this to be an addition in the integers, which are going to be equivalence classes. But the classes themselves don't have a fixed representative. You know, any representative could work. So if two people in different countries try to add up the same integers, well, they should get the same result even if they picked different representatives. We know that for positive ones, there's a natural choice for a representative, namely p comma 0, which is what I just proved in the lemma. But what about negative ones? I mean, there's also going to be a natural choice, but why do you pick a different one, right? So this is what we call in math when we're doing these sorts of things. We have to say that addition is well defined, right? Because I'm defining something on equivalence classes in terms of the representatives. So you need to verify that this doesn't depend on the representatives. Any representative will work. And the correct statement of what that means is that, oh boy. Okay. So what this means is that if, let me write this in the most concise way I know. X, Y, U, V are differences, right? I don't want to introduce 8 different natural numbers just for something unnecessary, so I'm going to refer to them with these variables. X, Y, U, V are differences such that X is D equivalent to U and sorry, and Y is D equivalent to V, then adding X and Y together should make no difference. It should be exactly the same or equivalent to adding those other numbers, right? It doesn't matter what representatives I pick. And the same thing happens for the multiplication. So proof is an exercise. Okay. This should be an exercise. Again, it's an exercise not interesting enough to be on the problem set, but something that you should know how to do, right? This is good practice. If you don't feel fluent proving things about equivalence relations, then this is one of many opportunities that you have to do this. Okay, so another lemma that is not difficult at all to prove, which is what you might expect. So this addition is associative and commutative. The order in which I do things doesn't matter, right? Another thing is that adding to a positive I'm just going to refer to them as positives. I mean positive differences, right? Adding two positives gives a positive. That is also immediately from the definition and satisfies cancellation law. Same thing with the natural numbers, right? You can cancel things on both sides if you have an equality. Exercise. All of these proofs follow either immediately from the definition, and it's less than a sentence to prove each, so I won't overwhelm you with a lot of technical details. Let's say this is an exercise 2. If you get stuck on this, of course, let me know. If I see that a lot of people are asking about this, I will simply cover this in the next lecture, no problem. Okay, now the part that gets a bit trickier is how do you define the product, right? Okay, well, now we define, just to add a little bit more detail, find a binary. Should have written that in the sum as well, but anyway. Now we define a binary operation that we will denote by this dot. Binary operation on n cross n, right? And how do we define that? Well, mn multiplied with pq should be the same as what? Let's think about this for a second. So m minus n, this is supposed to represent this number, right? So if I multiply two differences together, how should this behave? How should this behave? Well, you can just multiply this out, right? So this should be mp minus n. Sorry, let me write this in order. MP or plus NQ, right? This is the first part. And the other part are the negatives. So this is N, it doesn't matter, right? I think we can just do MQ plus NP. And that's how we define it. So there should be a difference between these two numbers. And these two numbers make perfect sense because I'm just adding natural numbers, right? I'm not referring to any sort of subtraction yet. And of course, you can verify the same properties. By this point, I think it might sound like I'm repeating myself, but this operation is well defined in the same sense that addition is well defined. It's associative, commutative, and distributes. Over addition. Right, this is the first thing. Second is that the product of positives is positive. Why is this important about positives? Well, I want this all of this to be consistent with the natural numbers. I want this to expand the natural numbers. So of course, if I add natural numbers, I should get the same thing that I would get if I had added just the natural numbers inside the integers, right? And over addition and satisfies cancellation. Cancellation law. Now, cancellation law, by the way, I should point out, this is all with respect to the equivalence relation, right? Not with respect to equality. Oh, big mistake here. Cancellation law is not true always, right? It is true, of course, for addition. Okay. Really struggling to do that. Cancellation law. So let's be a little bit more specific on what cancellation law means, right? Means that if m is not the same as n, because if they are, they represent the number 0, right? The difference between a number and itself is always representing the number 0. So I cannot cancel multiplication with respect to this. So cancellation law should be something like times PQ is equal to AB. Sorry. MN times AB. Then I need one more sentence. Then PQ is equal, but I don't know what equal means yet, is equal to AB, right? Equal in the sense that they're equivalent. So I can cancel MN on both sides as long as it's not representing the integer number 0 or the natural number 0, right? So this is also left as an exercise, but now we're done, right? We did everything we have to do. I guess, okay, wait, we're still missing the order, but before I do that, what is the integers? So an integer definition, should I write this as a definition? Why not? So now we are done, and I can actually tell you what an integer is. So an integer is integer is an equivalence class under this difference thing, right? Where should I call it x maybe to be consistent with earlier? Right, this difference. In other words, based on the previous notation that I introduced, the set of integers is the same as a set of natural numbers quotiented out by this equivalence relation, right? And that's it. I've introduced the integers for you. Now, of course, I need to repeat what the operations will mean in this case, but they will just be whatever they do on the representatives, they will do on the classes, right? So we extend addition and multiplication to these classes in the obvious way, right? How do you multiply two classes? Well, you take any two representatives, multiply them, and whatever object you get is the result. And we already proved that this is well defined. We already proved that this makes sense, right? Okay, and now we can actually make sense of everything else. Okay, so let me pause here briefly, and then I will tell you how to solve any linear equation of the form that I mentioned at the beginning. Okay, so I was saying the integers are just these equivalence classes. Now, I won't go into too much detail in how we would define the order and all that, or a very important thing about this is you want this structure to contain the structure of the natural numbers in some sense. And you already know what those are, right? It's basically the positive integers and 0. Those are representing the natural numbers. So let me tell you what I mean with like a diagram or something. The idea is that you have the equivalence class of 0, 0, and I'm going to drop the subscript because there's only one equivalence class I'm talking about right now. And of course, this has many representatives, right? This has basically, if I really wanted to expand this out, this would be the set of all n comma n, right? All of these differences are equivalent to each other, and they represent the same number, or the same thing, which I'm going to call, of course, 0. So this is precisely this thing right here, right? So the easiest representative is 0, 0. Then this is going to be smaller than the class of 1 comma 0, right? And what is 1 comma 0? Well, if you really want to know, you can also take 2 comma 1, 3 comma 2, and so on. So this is basically this, right? All numbers, all natural numbers whose difference is 1. And this, of course, represents the number 1. I think you can see where I'm going with this. So generally, you have this class k comma 0, which is representing, you know, etc., etc. But the interesting thing is what happens on the other side of this line. This is also a linear order, by the way, linear order. So the interesting thing is what happens on the other side. And what do you think happens here? What numbers are on that side? These are the positive ones, k comma sub c. And these are representing just the natural numbers in a way, right? Actually, this is like a theorem. First theorem about this is there is an injective function. And it's not just an injective function, it's going to be basically one of these, what are they called, like endomorphisms or something. Injective function, an embedding, right? It's an embedding that preserves all the structure from the natural numbers to the integers. It sends every natural number to the class represented by n comma 0. No, that's the positive integer that corresponds. And this embedding preserves everything, preserves all structure. And by all structure, of course, I mean addition, subtraction, and the order. Sorry, addition, multiplication, and the order, right? So what do you think happens here? What do you think happens on this side? Any ideas? Then I can finally tell you why I wanted the integers in the first place. most important fact about the integers is the fact that you can subtract things, right? So if x, y are integers, then there is